We're very happy to have Ankush Goswami speaking today, and he will be talking about the arithmeticity and quantum modularity for generalized Kontsevich-Zagier strange series.
Well, thanks, Ian, first of all, to invite me to speak here. And I would also like to thank you and Larry for organizing this wonderful seminar. So today I'll be speaking about, as Ian said, it's arithmeticity and quantum modularity for generalized Kontsevich-Zagier strange series. So let me first outline the two main goals of my talk today. So the first goal is going to be the following. I'm going to discuss my recent work on congruences of generalized Fishburn numbers related to torus knots, this family of torus knots, t3, 2 to the power of small t, where this small t is bigger than or equals to 2 at roots of unity. And then I'm going to discuss the quantum modularity of the Kontsevich-Zagier strange series associated to the same family of torus knots, and this is joint work with Robert. Okay, so let me start with the first goal of my talk, which is to discuss my recent work on congruences of these numbers. So let me first introduce the Fishburn numbers. So the Fishburn numbers xi of n are defined as the coefficients in the Q series expansion of this function f of 1 minus q. And this function f is nothing but the sum of q of n. And this sum runs over all non-negative integers. And this is the Kontsevich-Zagier strange series, which I'm going to discuss later in the slides. But for the time being, okay, so before I say anything about this function, f of q, this notation q of n is the standard hypergeometric notation, which is valid for all non-negative integers n, including infinity. And yeah, so I will discuss why fq is called a strange series later in my slides. But for the time being, fq is called strange because it satisfies a really strange identity, which only makes sense when q is a root of unity. Okay. Besides, this function f of q is a quantum modular object. I'm also going to discuss what is meant by quantum modular later in my slides. But for the time being, a quantum modular object is an object which has nice transformation properties when q approaches the root of unity. And this was proved by Zagier in 2001. Okay, so now the xi of n's, the Fishburn numbers, have very nice combinatorial interpretations. One can actually go to online encyclopedia of integer sequences and put this ID A002493, and one can actually see a host of different combinatorial interpretations for this number xi of n. And one such is that xi of n's count the number of linearized chord diagrams of degree n, and this is related to knot theory. Okay, so since in the first part of my talk, I'll be mainly interested in arithmetic properties, in particular congruences for various sequences of numbers. Let me start with the arithmetic properties of the Fishburn numbers xi of n. So their congruence properties were studied by Andrews and Sellers in 2014, but their paper came into print in 2016. And to state their result, we need to first consider the following set S with these three parameters P, R, and S. P is a positive, P can be any positive integer, R and S can be any integers. And you can define this set S, P, R, S, which is defined to be the set of all non-negative integers j in between 0 and P minus 1, such that j minus S is congruent to R times this pentagonal number mod P. In particular, if you just take R equals 1 and S equals 0, which corresponds to f of 1 minus q. We will see this later. So if you just choose S equals 0 and R equals 1, then this set SP10 will be the set of all integers in between 0 and P minus 1, for which J is congruent to a pentagonal number mod P. Okay, so this is the main theorem of Andrews and Sellers from 2016, and it states that if P is a prime and J is an integer in this set, from consisting of elements from 1 all the way up to P minus 1 minus maximum of the set SP10, then for each such J, you will get these congruences for the Fishburn number. That is, for each J in this set, you have xi of Pn minus J is divisible by P, and this holds true for all positive integers n. Okay, so for example, we can now take p equals 5, and you can easily check that this set starting from 1 all the way up to p minus 1 minus maximum of sp10 will consist of exactly 2 elements, 1 and 2, and thus you get 2 congruences from Andrews-Seller's theorem, modulo 5. Okay, so when p is 7, you get only one element in this set, and that is j equals 1, and you only get one congruence mod 7. Similarly, if you choose p equals 11, you get 3 elements in that set, j equals 1, 2, and 3, and that gives you 3 congruences mod 11. So in this way, you can go on taking different prime values p and get congruences, provided this set is non-empty. If this set is empty, you will not get any congruence, and that happens precisely when p is 23. So if you just choose p equals to 23, then this set becomes empty, and you do not get any congruence for the Fishburn numbers mod 23. Okay, so in 2015, shortly after Andrews and Sellers published their work on archive, Garvin generalized Andrews and Sellers' result. But before that, he did some computation, and his computation suggested the following congruences mod 23 for the Fishburn numbers. And these are the congruences mod 23 for the Fishburn number xi. And after he generalized Andrews and Sellers' result, he actually showed that this is indeed the case. I mean, mod 23, the Fishburn number satisfies these congruences. Okay, so to state Garvin's result, we need to define the RS Fishburn numbers, which are denoted by xi with subscripts R, S of n. And this is defined as the coefficients in the Q series expansion of the left-hand side, where you have 1 minus q to the power of s times f of 1 minus q to the power of r, where r is any non-zero integer and s is any integer. Okay, and then you have to consider the set S star PR of s, PR and s, which is defined as the set of all values j in the set SPRS for which this condition is satisfied, like 24 times j minus s should not be congruent to minus r mod p. So this is the set S star. I mean, you can easily say that this set S star is a subset of SPRS. So there is a good chance that if this set is empty, this set might not be empty. Okay, and now we can state Garvin's result. So if p is a prime and r is an integer such that p does not divide r, and s is any integer in between 0 and p minus 1, and if j is any element in between 1 and p minus 1 minus maximum of s star PRS, then the RS Fishburn numbers xi RS of pn minus j is divisible by p, and this holds true for all positive integers n. Okay, so this is Garvin's result, and yeah, and as you can see in the 23 case, when p is 23, one can easily see that 22 belongs to S2310, and so you do not get any congruences using Andrews and Sellers. However, 22 does not belong to S star 2310, and you get congruences using Garvin's theorem. And these are precisely the congruences that you see here. Okay. Okay, so some other congruences which are obtained via Garvin's theorem are as follows. So if you choose r equals 2 and s equals 0, you get this congruences mod 7. If you choose r equals 3 and s equals 0, you get this congruences mod 19. And if you choose r equals -1 and s equals 0, you get this congruence mod 5. And this last congruence answers a question of Andrews and Sellers in their paper. So this was a conjectured congruence in Andrews and Sellers' paper. So his result also gives this congruence. Okay, so the next natural question would be, would all of this congruence hold for prime powers? And this was one of the questions in Andrews and Sellers' paper, and this was answered in the affirmative by Straub, who extended all of the congruences of Garvin to prime power modulus. Okay, and to state his result, we recall that if you take any rational number n, then it has a unique p-adic expansion which can be written in this form: n equals the sum of nkp to the power k, where this nk is basically an integer in between 0 and p minus 1, and this new p of n is the p-adic valuation of n. And p-adic evaluation of n simply means that if n is the rational number, you write it in the lowest form, then nu p of n is the highest part of p, such that p to the power of nu p of n will either divide the numerator of the fraction or the denominator of the fraction. Okay, so, and then we also write nk in this form. So nk is written as digit with subscript k of n semicolon p. So this is the notation for nk. Okay, and then we can state Straub's result, which states that if p is a prime and r and s are integers such that p does not divide r, and if j is any integer in between 1 and p minus 1 minus maximum of SPRS, then this RS Fishburn numbers, which are denoted by xi RS, satisfies this congruence mod p to the power of L. And the second part of and this holds true for all positive integers n and L. And the second part of the theorem states that if p is strictly bigger than 5, that is if p is 7 and onwards, and the triple PRS satisfies this condition that the coefficient of p in the p-adic expansion of s minus r over 24 is not equals to p minus 1, then one can replace the set SPRS by the smaller set S star PRS. So this is Straub's result, and using his result, one can get these congruences. So if you take p equals 5, r equals 1, and s equals to 0, then you get these congruences mod powers of 5. And we can see that this xi1 of 0 is nothing but the Fishburn numbers. So yeah. Okay, also, if you take p equals to 7, then you get these congruences mod 7 to the power of L. And yeah, and you take, if you take p equals 19, you get this congruence mod 19 to the power of L for xi3 of 0. Xi3.
I have a quick question, I
Yeah.
guess, about these. Do the RS Fishburn numbers have a nice like combinatorial interpretation, like these core diagrams or something like that?
Not that I know. Yeah, that's a good question. Yeah, not that I know. RS Fishburn. Yeah. Yeah. Even if you just put s equals to 0, I still don't know if there is any combinatorial description for xi r0. So if you look at the definition, so this is RS Fishburn numbers. If you just remove this factor 1 minus q to the power s, I don't know if xi r0 n has any combinatorial description.
Is there, does Garvin give like a reason why he chooses to generalize them in this way? Like a
Yeah, mainly I think it's a first of all it's a general thing, general consideration, then the numbers, or then the generating function considered by Andrews and Sellers. And the second thing is by choosing this form of the function, he's able to prove the last result, which is xi of minus 105 is of 5 and minus 1 is congruent to 0 mod 5. And this was a conjecture in Andrews and Sellers' paper. Okay, and other than that, yeah, it also, more than that, it is also about this set S star PR of S. So with this condition, he is able to reduce the set to a smaller set for some primes P. So for example, as I've said, like if you choose P equals to 23, then 22 belongs to that set, the set S, but 22 does not belong to the set S star. And yeah, and he was able to get this additional congruences mod 23. Which
so for example, though, like yeah. If you plug in, like, instead of plugging in 1 minus q into the Fishburn series, if you plug in like 1 plus q divided by 1 minus q, that's still that's I mean, that's natural in some sense because it's like a Cayley transform, and it's still, if you expand it out, counts something, has a combinatorial thing. So I was just wondering if like Garvin gave some motivation through like,
okay, so as far as I remember, his paper does not discuss f of, you said f of 1 plus q divided by f of 1 minus q, right? Oh, f
yeah.
Of 1 plus q
so I think it was Hannah Burson who actually pointed this out to Larry and I when she gave her talk, that Bruce Burt has, I don't think about specifically the series, but expanded some quantum modular type things out like that, and it was natural because it was a Cayley transform type thing. And if you use that for F1, you can plug it into OEIS and see it counts like Fishburn matrices with decorated in some way. So it does have.
I don't think
thing.
I don't think Garvin discusses this even for some special case, like if you take f of 1 minus q squared,
Mhm.
yeah, he does not discuss any combinatorial meanings of these numbers as I
Okay.
of 2, 0. Yeah,
Okay. Thanks.
yeah.
Okay.
But yeah, it's interesting. I will have to take a look. Yeah. Okay, so yeah, so uh, these are the three family of congruences that you get using. Okay, where was I? I was discussing this, right? And then yeah. Okay, so yeah, so these are the congruences that you get using Straub's result, and this. So the first one is the congruence for the Fishburn numbers, which also holds modulo powers of primes. So in this case, p is 5. And then you can also choose different values of R and S, and you get different congruences for different powers of primes. Okay, so in a recent work, what I did was I extended all of these results to any root of unity. So for example, so to state my result, uh, let zeta of n be an nth root of unity, and then you consider this function zeta of n minus q to the power of s, f of zeta of n minus q to the power of r. You consider this function, and then you do it, and then you write the q series expansion of this function with the coefficients being xi with subscripts r s capital N of n. And then I would like to see if there are any congruences for this coefficient xi with subscripts r s capital N of n. But before I do that, or before I state the result, we'd have to just note here that this xi with subscripts r s capital N of n may not be an integer, but they are in the cyclotomic ring of integers. And so when I say xi of r as capital N of n is congruent to 0 mod m, where m is any positive integer, I mean that there exists some other element in the same cyclotomic ring of integers such that one can write this xi r s n of n as m times this u r s n. Okay, so with this convention, I can now state the theorem, and it states that if p is a prime bigger than or equals to 5, and if n is a natural number and r and s are integers such that p does not divide r. So these assumptions are almost same as what we have in Straub's theorem or Garvin's theorem. So if p does not divide r, then for all natural numbers l and j in this set, in the set consisting of elements from 1 all the way up to p minus 1 minus maximum of that, we have these congruences for the generalized Fishburn numbers xi r s n modulo p to the power of l. So yeah, so this is the first part of the theorem. And the second part of the theorem states that if n, which corresponds to the root of unity, if capital N divides Rp, and if the triple PRS satisfies this condition, the same condition that we have in Straub's theorem, then one can replace the set SPRS by the set S star PR of S. So yeah. So for example, if you now take n equals to 2, this corresponds to the second root of unity. So, and this corresponds to the function f of minus 1 minus q. Okay, then for all natural numbers l and n, you will have these congruences. So xi of 102. So this is capital N. So the last entry here is the value of capital N, and then you have r equals 1 and s equals to 0. So xi of 102 satisfies these congruences mod 5 to the power of l. Similarly, if once again, if you choose n equals to 2 and choose a different prime, of course, then you get these congruences for xi 102 mod the power of 7 to the power of l. Okay, and then what you can do is you can also choose the same root of unity n equals 2, but now you choose r equals 2. If you now choose r equals to 2, then for all natural numbers l and n, you get these congruences mod 7 to the power of l. And similarly, you get this congruences mod 11 to the power of l. Okay, so these are the examples coming out from this theorem. Okay, and now I'd just like to give you 2 steps in the proof. I mean, there are I don't want to go into the technicalities of the proof, but this is just the sketch of the proof. So first, what you have to do is you have to follow the strategy as in the proofs of Andrews and Sellers or Garvin or Straub. And then the main difference in this proof and in all the other proofs is the fact that one has to use the strong divisibility result of Algren and Kim from 2015 for the dissections of the partial sums of FQ, which says that like if you have like if you take the partial sums, if you take the dissections of the partial sums of f of q, then it is divisible by q shifted factorial rather than a power of 1 minus q, which was conjectured by Andrews and Sellers in their paper. And in Andrews and Sellers' paper, they use this weak divisibility result, which is about like these dissections are divisible by 1 minus q to some power. So yeah, so the main key difference is the fact that one has to use the strong divisibility result of Algren and Kim in contrast to the weak divisibility result of Andrews and Sellers in the proof. Okay, so all right, so now we can discuss the generalized Fishburn numbers for the family of torus knots t3, 2 to the power of t, where t is bigger than or equals to 2. Okay, and in order to do so, we have to consider the Kontsevich-Zagier series associated to the family of torus knots. So the same family of torus knots that we saw earlier, and it is defined by this this function. So you consider ft of q, which is defined by this expression in the right hand side, where yeah, it's okay. So I'll just tell you what these things are, like h double prime t, h prime t, mt, and the I. So mt is basically 2 to the power of t minus 1. I star is the characteristic function, and this h prime, h double prime, and a of t that you have here are defined as this, are defined through this piecewise definition for t even and t odd. All right, and then you have this binomial, the q binomial coefficient, which is defined as usual by this ratio. All right, so okay, so last week Robert explained how FTQ, which is the Kontsevich-Zagier series associated to the family of torus knots, can be extracted from the non-cyclotomic expansion of the Color-Jones polynomial, which was obtained by Conan in 2016. So I'm not going to discuss any knot theoretic connection of this function ft of q. Okay, an important thing to see here is this ft, the function ftq generalizes fq in the sense that if you choose t equals to 1 and adopt usual conventions in the sum and products, like the empty sum and the conventions of empty sums and products, then you can easily see that f1 of q is equals to fq, where fq is the original Kontsevich-Zagier series that we saw earlier. And now one can define these generalized Fishburn numbers, xi t of n, which are the coefficients in the q series expansion of ft. So if you do a q series expansion of ft of 1 minus q, then the coefficients will be xi t of n, and these are called generalized Fishburn numbers. Okay, so now if you choose t equals to 2 and write the first few terms in the q expansion of that, you'll see this. You'll get this 1 plus 3q plus 11q squared and so on. And similarly, if you choose t equals to 3 and write the q expansion of f3 of 1 minus q, the first few terms is going to look like this. Okay, so now we're going to discuss. So this is a natural question. What about congruence properties for this generalized Fishburn number xi t of n? So in 2000, I mean, in this year recently, Bijavi and others have studied congruences for these numbers xi t of n, and their paper is going to appear in print in 2021. And to state their result, we need to introduce a few things. So first of all, we'd like to define this function chi t of n, which is a periodic function of period 3 times 2 to the power of t plus 1, and it is defined only on 4 residue classes, mod 3 times 2 to the power of t plus 1. Otherwise, it is 0, as you can see. Okay, and then you define this set st chi t p, where you can actually define this set for any positive integer b, but for the time being, let us assume that p is prime. And then you define the set st chi t of p to be the set of all positive integers in between 1 and p minus 1, such that this j should be congruent to this rational number mod p, and n should be such that chi t of n is not equals to 0. Okay, so now the main result of Bijavi and others states that if p is bigger than or equals to 5 is a prime, and j is an integer, a positive integer in this set, then you have these congruences mod powers of primes for the generalized Fishburn numbers it, and this holds true for all positive integers l and n, and this is true for all t bigger than or equals to 2. Okay, so for example, if you choose t equals 2 and p equals 5, then you get this congruence for xi of 2 mod 5 to the power of l. Similarly, if you choose t equals to 3 and p equals to 7, you get this congruences mod 7 to the power l for xi of 3. Okay, and so on. Okay, so in recent work, I also extended all these congruences at roots of unity. So once again, what you have to do is you have to consider the expression in the left, which is zeta of n minus q to the power of s, ft of zeta n minus q to the power of r, where zeta n, as before, is a root of unity, is an nth root of unity, and r and s are certain integers. For the time being, you can just assume that s is any integer and r is a non-zero integer. And then you write the Q series expansion of the left-hand side. Then the coefficients are given by this thing, xi with subscripts r, s, and t. I forgot to put an n here. So of n times q to the power of n. And now the natural question is, what about congruences for these numbers, xi, r, s, and t? So in order to find the congruence, you have to first define a similar type of set that Gavin defined in his proof, that Gavin defined in his paper. So you define the set st chi t star of PRS as the set of all element j belonging to st chi t PRS such that this condition is satisfied mod p. So this is precisely the set that Gavin considers. So if you just put t equals to 1, then you will see that this S1 chi1 star PRS is the same as S star PRS in Gavin's work. Okay. And now we have to define, now for any t bigger than or equals to 2, we have to, our theorem does not hold true for all primes. So so our theorems only hold true for certain families of primes. And let me first define this set of primes by. So the first set of prime is denoted by P1, and it is a set of primes which satisfy the condition that P is congruent to 1 mod this thing. P2 is the set of primes which satisfy the condition that P is congruent to -1 mod 3 times 2 to the power t plus 1. And P3 is the set of primes satisfying the condition that P is congruent to R1t mod 3 times 2 to the power t plus 1, where this R1t is defined by this piecewise definition for t even and t odd. And similarly, P4 is the set of primes which satisfies this condition that P is congruent to R2t mod 3 times 2 to the power of t plus 1, and then R2t satisfies this piecewise definition. Okay, so before stating the main result about congruences for the numbers xi, r, s, and t of n, we have to first note that this xi, r, s, and t of n may not be integers, but they belong to the cyclotomic ring of integers. And so once again, when we say that xi, r, s, and t of n is congruent to 0 mod m, where m is a positive integer, I mean that there exists an element in the cyclotomic ring of integers u with these subscripts, such that you can write xi with subscripts r, s, and t of n as a product of m and u. So this is the convention. And now we can state the main result, which is if t is bigger than or equals to 2, p bigger than or equals to 5 is a prime, and capital N is any natural number, and r and s are integers such that p does not divide r, then for all j belonging to this set, we have these congruences for this generalized Fishburn numbers xi, r, s, and t, mod p to the power of l. And this holds true for all integers l and n. Okay, and now the second part of the theorem is important, because here I'm replacing the set st chi t by st chi t star. And to do so, we only have to, I mean, the second part of the theorem only holds true when P belongs to any one of these four subsets of primes. So if P belongs to any one of the subsets of primes, and as we saw in previous slide, and if N divides Rp, and the triple PRS satisfies this condition, the digit, I mean, the coefficient of, so this thing simply means that the coefficient of P in the p-adic expansion of S minus AR by B is not equals to P minus 1, then one can replace the set S with S star. So in Garvin's case, when you put T equals to 1, the union of P1, P2, P3, and P4 becomes the set of all primes. But this is not the case when T is bigger than or equals to 2. So we only have the second, so when T is bigger than or equals to 2, the second part of the theorem only holds when P lies in any one of these sets. Okay. Okay, so a few examples. Okay, so if you just take S equals to 0, T equals to 2, N equals to 2, you get these congruences for the coefficients of F2 minus 1 minus Q and F3 minus 1 minus Q. So these are the congruences for xi 1022 modulo 5 to the power of L, and this corresponds to R equals 1, S equals to 0, T equals 2, and N is also equals to 2. And similarly, you get the same congruences, and you get similar congruences for xi 1023. So here T is 3, and this is modulo 7 to the power of N. Okay, so any questions so far before I go to the proof, the sketch of proof? Okay, so the sketch of proof. Okay, so the first thing to do is to proceed as in on Andrews and Sellers or Straub or Garvin, and then we have to use the strange identity for FTQ, which was established recently by Bijavi, Boden, Myers, Osborne, Rushworth, Tronsgaard, and so. And then one has to apply the strong divisibility result of Algren, Kim, and Lovejoy from 2019, which is again the same thing. Like if you take the p dissections of the partial sums of ft of q, then it is divisible by q shifted factorial rather than 1 minus q some power of 1 minus q. Okay, and now for the second part of the theorem, which is if we want to replace the set st chi t by the set st chi t star, then we have to establish a key result which generalizes that in Garvin 2015, and this key result is about showing that that certain p dissections of the partial sums of ftq are divisible by p. So this is the key result, and if once one establishes this thing, one can actually replace the set st chi t by the set st chi t star. And as I said earlier, unlike in the case of Garvin, this divisibility only occurs for 4 disjoint families of primes described in 1 to 4. And this is precisely, I mean, as I said, like when t is 1, this union gives you all the set of primes, I mean, all the primes. And when t is bigger than or equals to 2, you have only 4 disjoint families of primes where the theorem holds. Okay, and then what you have to do is you have to use Kumar's theorem, and which is about p-adic valuation of binomial coefficient, and that completes the proof of the theorem. Okay, so that completes the first part of my talk. So how much time do I have?
You have, if you want, all the way till noon, but at any time between 11:50 and noon is good. So you have about between 15 and 25 minutes left.
Okay. Okay. All right. So this completes the first part of my talk today. Okay. For the second part of my talk, the second part of my talk is to discuss the quantum modularity of this function ft of q, and to do that, we need to introduce the definition of quantum modular form, which was formally defined by Zagier in 2010. So a quantum modular form of weight k, where this weight can be either integer or half an integer, is a function g from the set of rational numbers to the set of complex numbers, for which this function r gamma, which is given by this difference, so the difference between g alpha and this quantity c alpha plus d to the power of minus k times g of this expression. So this is r gamma of alpha, which is defined from q minus gamma inverse I infinity to C should extend as a real analytic function on the projective real line, excluding a finite set of points. And this should hold true for each gamma in SL2Z. Okay, so one can suitably modify the definition of a quantum modular form by restricting the domain of R gamma to appropriate subsets of Q, and also allow certain multiplier systems and transformations on subgroups of SL2Z. Okay, so yeah, so in the same paper in 2010, Zagier also introduced 5 examples, out of which the most influential one of the most influential one is the Kontsevich-Zagier strain series FQ, which Zagier studied in 2001. And one of the main reasons why FQ is called strange is because it does not converge anywhere inside or outside the unit disk, but it is well defined when Q is a root of unity, in which case it is finite. Okay, so let me just recall, we've already discussed f of q, but just for the sake of completeness, okay, so just recall that fq is defined via this series, which is the sum over all n bigger than or equals to 0 of q of n, and this q of n is the standard q hypergeometric notation. And then this f of q satisfies a really strange identity, and this was proved in the 2001 paper of Zagier. He showed that this f of q, this is not an equality, but this is an equality within quotes. So f of q is like within quotes equal to minus 1/2 of this thing, which is a partial theta series. And this equality within quotes means that the two sides agree to all orders when q is a root of unity. So the two sides the two sides become equal only when q is a root of unity. Otherwise, they do not make sense. Okay. Okay, so what Zagier did was he showed that the right hand side of one this right hand side of one can be viewed as the Eichler integral of the Dedekind function, which is a modular form with 1/2, which is also a cusp form. And then he showed that this Eichler integral has quantum modular properties, which via one can show that FQ is also quantum modular. So this is the main idea behind showing the quantum modularity of FQ. He first showed that the right-hand side of one can be viewed as an Eichler integral of the Dedekind function, and this Eichler integral has quantum modular properties, and via one, these quantum modular properties are transferred to f of q. Okay, so the next question is, the next natural question is, what about quantum modularity of ftq for t bigger than or equals to 2? So for that, we once again need a strange identity that we have for f of q. And this strange identity was again established by Bijawi and others recently, and it looks like this. So ft of q is equals to, within quotation, minus 1/2 of this partial theta series. And this equality within quotation means the same that we saw in previous slide. And to state the result, we define this congruent subgroup gamma 1 of n for a natural number capital N, and this is the set of all 2 cross 2 matrices in SL2Z where the lower left entry C is divisible by n, and the diagonal entries are congruent to 1 mod n. And then we just set, for notational ease, we just set ST equals to this fraction. Then we have this result that for an integer t bigger than or equals to 2, and if alpha is a rational number, and if you define this function phi t of alpha as this factor multiplied with ft of e to the power of 2 pi I alpha, then this function phi t of alpha is a quantum modular form of weight 3/2 on this set. And this set is nothing but the set of all rational numbers which are equivalent to 0 or I infinity under the action of this subgroup gamma 1 of 3 times 2 to the power of t plus 2. And yeah, and this is a quantum modular form with respect to this subgroup gamma 1 of 3 times 2 to the power of t plus 2. Okay, so now we can just sketch the proof of this result. Okay, so what we have to first do is we have to first consider this partial theta series, which I denote by theta with subscript t of z. And then you have to define the Eichler integral of theta t of z as follows. So we denote it by theta t tilde of z, which is the integral from z, which is the integral going from z to I infinity of theta t of tau times tau minus z bar to the power of minus 3/2 of d tau. And now what we have to show is we have to show that this theta t of z has exponential decay at the points z equals to 0 and I infinity. And it also satisfies a modular transformation property on this subgroup. And these facts imply that theta t tilde z is well defined on the upper half plane, including the set, including the subset of rational numbers a 3 times to the power of t plus 1. And then what you have to do is you take any z, either in the upper half plane or in the set a 3 times to the power t plus 1, and then use contour integration to show that this Eichler integral is nothing but this series involving the incomplete gamma function. And when you put z equals to alpha, where alpha is an element of alpha is an element of a 3 times to the power of t plus 1, then you can show that this theta t tilde of alpha is some factor multiplied with theta t of alpha, which basically is the partial theta series which we have in the right hand side of the strange identity. So basically the Eichler integral is essentially the right hand side of the strange identity, or when alpha belongs to this set. Okay. And then finally you show that this theta t of alpha satisfies this condition, or this transformation, that theta t of alpha minus theta t slash, so this is the Peterson slash operator. So this is theta t slash 3/2 comma chi t of gamma of alpha is r gamma t alpha, and this r gamma t alpha is a C infinity function and is real analytic in this set, and it is given by this integral. Yeah, so I think, yeah, so this completes the proof. Yeah.
Great. Yeah, let's thank.
Yeah, I think I went really fast.
No, I think it's good. We have time for questions, but yeah, let's thank Ankush for his talk first. So, and does anyone have any questions? I have like a quick one, I guess, again, about the proof here at the end. Can you say a few words about the modularity of this theta sub t, the thing that you end up taking the Eichler integral of?
Okay.
So to begin, right, we know that like for the t equals 1 case, we get essentially like the Dedekind function, nice modular. Yeah. Are these theta sub t's similarly nice in that way?
Oh yeah, that I mean, you can write theta t of z as a product of like, I think it's as several products. You know, the first factor is going to give you an eta function, but the rest is generalized eta function.
Okay.
So you can write theta t of z as a product of one eta factor, and the rest is generalized eta factors. Okay. Yeah, but yeah, so that is the thing.
So I'm assuming though that is where like the nice like that the error to modularity, the R.
Yes, it is actually the transformation property of theta t of z that gives you this relation, that theta, the big theta t of alpha, this difference is this. Okay. So yeah, so this relation in point 5 comes via the transformation property of this theta function, theta t of z. Yeah.
Thanks. Do we have any other questions? Right. If not, let's thank Ankush again for his talk.